Next we come to the geometrical and the optical isomerism shown by square planar complexes. Now I had told you about square planar complexes. Square planar complexes are like all the ligands as well as the metal atom, they are present in one plane, right. So there can be a plane of symmetry which is bisecting all of them equally, all of the atoms or all of the ligands as well as the metal atom in half. So usually square planar structures, they do not show optical isomerism because they have a plane of symmetry. Geometrical isomerism, some of them can show, some of them cannot show, that depends upon the ligands that they have, but optical isomerism most of them don't show. So now let's go and see the various cis pairs and the trans pairs for your square planar complexes like we did for our octahedral complexes. So again, cis pairs are the ligand pairs which are at a 90 degree. So the ligands 1 and 2, they are at an angle of 90 degree. So that's 1, 2. Again 2 and 4 are also at an angle of 90 degree. 1 and 3 are also at an angle of 90 degree, as well as 3 and 4 are also at an angle of 90 degree. So all of these are cis pairs. Cis pairs, and therefore next we go to trans pairs. So we already know trans pairs are the ones which are present at 180 degree. So that's your 2 and 3 as well as 1 and 4. These are the ligands which are present at 180 degree. Next we will take some of the general type of complexes of square planar and we will try to see what will be the geometrical isomerism exhibited by them. Mostly they are not going to exhibit any optical isomerism. If there are any exceptions, we will come to that. This is the first square planar complex. In this all the ligands are of the same type. So it is MA4. Obviously there is only going to be one possible pair, AA. So in this A is trans to A is trans to A. So there can be no geometrical isomer because there can be no possible pairs. So it cannot show any geometrical isomerism, it cannot show any optical isomerism as well. If you look at its calculations, you will write that the number of geometrical isomers is equal to 1. The number of optical isomers will be 0 because it is not optically active. The number of enantiomeric pairs is also going to be 0. And the number of stereoisomers is going to be the number of optical isomers, which is 0, plus the inactive possible pairs, which is 1. So that's equal to 1. So this was the isomerism which is possible in the square planar complex of the type MA4. Now next we come to the geometrical and the optical isomerism shown by the square planar complex of MA3B type. As I have already said you, optical isomerism is not shown, so we will focus only on the geometrical isomerism part. So MA3B also has this possible pair, and notice how it is only going to be the possible pair, there can be no other possible pairs. In this A is trans to A is trans to B. Again this is optically inactive because the plane of symmetry is passing right through the entire molecule. So this is also optically inactive. So if you say what are the number of geometrical isomers, you will say 1, but it will not show any geometrical isomerism. Then the number of optical isomers are going to be 0 because that was optically inactive. So the number of enantiomeric pairs is also going to be 0, which makes the number of stereoisomers equal to 0 plus 1, which is equal to 1. Next we come to the square planar complexes of the type MA2B2. This is the first possible pair in this. A is trans to B, A is trans to B. Again this is optically inactive. All square planar complexes are optically inactive unless there are some exceptions. And we have A is trans to B and A is trans to B. In the previous one there was A is trans to A. So in the previous one we had A is trans to A as well as B is trans to B. So in this case A is trans to A. So you can say that this is a trans isomer. Whereas in the next case you can say that this is a cis isomer. So these are the only two possible pairs for this type of complex, that is MA2B2. So the number of geometrical isomers as we saw was 2. The number of optical isomers is 0 because again there were no optically active pairs. So that makes the number of enantiomeric pairs also equal to 0, which now we come to the number of stereoisomers. So the number of stereoisomers is optical isomers plus the inactive pair, so that's 2, so this is equal to 2. Next we come to the square planar complexes of the type Mabcd. In this all of the ligands are different. There are so 4 different ligands, and this is the first possible pair. In this, A is trans to B, C is trans to D. So there are no trans pairs getting repeated, as well as the same ligand is not trans to each other, but again this is still going to be optically inactive because the plane of symmetry is there. It is passing right through all of the A, B, C, D and M, and it is bisecting them into half. So this is still optically inactive. A is trans to C and B is trans to D. In the next possible pair, we have A is trans to D, B is trans to C. So the total number of possible pairs for this complex are 3. So when we say the number of geometrical isomers, we are going to write 3. The number of optical isomers. The number of optical isomers is going to be 0. So if the number of optical isomers is 0, that means the number of enantiomeric pairs is also 0. Therefore, the total number of stereoisomers is the number of optical isomers plus the inactive pairs, so that's equal to 3. So these were all the possible isomers which can be exhibited by Mabcd.